The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I think it is most fitting that we would close these two sessions about the legacy of Dr. Corley by having his advisor from graduate school. He certainly is the person that has known him the most, the longest. I know that Dr. Corley stayed in touch with Professor Sozen all along, although Professor Sozen left Committee 318. And Gene Corley continued. He always continued to get in touch with him, and it's a pleasure to introduce Dr. Mete Sozen.
Thank you very much, Basil. And I thank you all for having the patience to stay with us to remember Gene Corley. And I will try to take as little of your time as possible and try to finish this thing off. But I think I should start with a confession. Dr. Fierato gave me months to prepare this presentation, but I couldn't do it. I was in denial. Gene's passing away was too sudden. He was too loved a friend. And every time I sat down to put a few notes together, I would go into a state of depression. And this went on. I'm not kidding. For a while I was thinking, although I don't trust them, but I was thinking whether I should go to a psychiatrist to get out of it. But last week, everything cleared up for me, thanks to a colleague in geotechnical engineering. He was giving a talk about what was needed. And he emphasized that engineers treated the problem of liquefaction too simply, by simply using the blow count. And he thought it should be done in a much more complicated way. And he asked for only $250,000 to do it. At that moment, I'm not kidding, suddenly Gene was seen unto me. And he told me, doesn't this man know that if you're going to be wrong anyway, you should be wrong the simple way rather than the complicated way? I think he was right. I don't think I'm misjudging him. And then it also occurred to me that instead of grieving for his loss, I should be joyous. I should be happy that I knew him for over 50 years and that he was a trusted friend and a dear person. You see, our lives were intertwined in various ways. Yes, he was my student, but then he became a very close friend. And it was always wonderful for me whenever I found something in the lab that disturbed me, that I could call him and ask his opinion. And he often gave me the opinion unabashedly. And I'm glad Randy mentioned the business of the shearhead. I tried to get that thing out of the code several times, but he stood his ground. And in the rewriting of chapter 20, I tried to get some definition of a shear failure and a bond failure into the code, and he stood his ground. Because he wanted to define it depending on the case that he was handling, ultimately. But he also, going down to trivial matters, he also complained that when he was working on his thesis, I could give him appointments only at 2 o'clock or 3 o'clock in the morning. He never stopped complaining about that, and I never stopped complaining about the fact that he used to smoke. But going down to lower levels, now can you believe this man who always wore a tie teaching me how to do the monkey dance in Tokyo? So he had a very wide range of talents. I remembered once we were working in New York after the World's Fair, testing one of the buildings with Don Magura. And our test had been delayed because the local electrical laborers union had said that we couldn't use our own instruments unless we hired 6 of them to stand around while we used the instruments. Well, we had to do it ultimately. But the test ended up at about 3 o'clock in the morning, and at around 2 o'clock, Gene told me, look up, look up. And I looked up, and I saw the biggest fire that I'd ever seen in the sky that went over at least 30 degrees. And see, these were the post-Kennedy years. And we all considered very seriously the possibility of an atomic attack on the United States. And I remember Gene telling me, and we had to be in New York. But fortunately, we survived that. We also survived a sinking in Florida once, when he and I were sailing together and managed to capsize the sailboat. But anyway, as I said, our lives were intertwined. I do remember very much that our youngest grew up on cold milk because Gene and Lind advised us not to bother warming up the milk to body temperature. And we used to call it the Scott Corley special, Scott being his youngest child. But look, I should be telling you about his technical prowess. And in a way, I'm glad that everybody ignored it. Gene worked on a job, starting on it when he was barely a graduate student, and I would like to talk to you about that. But before I go into it, let me give you my definition of a structural engineer. In the 50s, I had read a book by an English writer called The Borgia Testament. It's not irrelevant to what I shall be talking about. It was supposed to be the statements of Cesare Borgia about his life. And you probably know Cesare Borgia was the son of Alexander VI, the Pope. But of course the Pope was not married. It was a miracle. And he ended up being essentially the military leader of the Vatican and fought against the dukedom of, I forget where, but the kingdom of Venice, especially. And at one time he hired Leonardo da Vinci, who was still called Leonardo da Vinci at that time. The da was not in it. And in his memoirs, he talks about him like this. He says, Vinci was a handsome man. He certainly played the lute and sang very well. He also drew very finely. But he claimed not only to be an artist, but a practical man. And he wanted me to employ him as my engineer. I gave him the job, though I never felt very happy about it. I prefer my engineers to be engineers and not engineering lute players. Vinci was never really a success as an engineer. He certainly had an ingenious mind and a very fair amount of technical information. But he was not reliable in the day-to-day details of his work, and he had an irritating knack of making simple problems difficult. And you know, I find a simple statement an inverse definition, but the best definition of what a structural engineer should be. He should be reliable in the day-to-day details of his work and make difficult problems simple. Should be, I'm sorry, I'm repeating it. And I think Gene fit those standards elegantly. and I would like to talk to you only about one aspect of his work in which he did make a difficult task very simple, and I'm surprised that I'm the only one who knows this. It's about time-dependent deflections of reinforced concrete beams. Look, you know better than I do that if you deal with time-dependent effects in reinforced concrete, you're in trouble, one way or the other. I mean, time is a factor. Age at loading is a factor. Size of the beam is a factor. Shape of the beam is a factor. The mix can be a factor. The aggregate, the type of aggregate can be a factor as to how much creep or how much shrinkage you're going to get. The possibility of carbon dioxide in the environment can affect the shrinkage. Humidity is certainly a factor. Temperature is a factor, and it's got a lot of scatter. Amount of tension reinforcement is a factor. The amount of compression reinforcement is a factor, and I can go on forever. Seasons, of course, make a difference as to how much time-dependent deflection you're going to have. It's the fuzziest problem that you can deal with. And contrary to what that geotechnical engineer said, this is a problem that needs to be solved simply as it can be. And Gene did that very early in his graduate career. Look, take what we do with respect to deflection. We assume a linear strain distribution, and it's a little bit humorous because we admit that there is no strain beneath the neutral axis, right? But we still talk about a linear strain distribution. And as I will tell you later, it works for short-time deflection. And the deflection is proportional to that angle change, which is indicated as initial over there. It's fairly simple. If you have creep that is a multiple of the initial strain, then the strain distribution, according to Gene, becomes ideally, as I've shown by the broken line. Yes, it doesn't rotate about the strain in the steel, but it's close enough in a problem like this. And if that is so, he could tell that the errors he makes in creep are not as critical as they might be, because you divide the creep strain by the overall depth of the beam. So all you have to do is define the creep and the shrinkage. And he defined the creep as a function of the initial strain essentially as 3. I had suggested pi, but he thought that was too complicated. Minus amount of compression steel divided by the amount of tension steel, but more than 2, between 3 and 2. And then the increase in unit curvature related to creep was simply epsilon creep over d. Very simple. The increase in unit curvature attributed to shrinkage, well, ideally, if you have equal amounts of tension and compression reinforcement, you shouldn't have any curvature due to shrinkage. That's romantic to believe, but hey, it's not too far away from the truth. So what he did, was to define the shrinkage as rho minus rho prime over d divided by 30. One significant figure. Combining them, he of course had to make a sophisticated assumption about the change with time, and he said the 2-year, if you consider the 2-year total, then the fraction of that 2-year total would be the natural log of t in days plus 1, and I think you know why 1, because when t is 0, things blow up otherwise, divided by 8, again, one significant figure. And he combined them all, and he took results from, if I remember correctly, 9 different investigations. And you know that these investigations had simple and continuous spans, rectangular and T sections, with and without environmental control somewhere outside, age-jet loading from 2 to 28 days after casting, and with and without compression reinforcement. All the variables were in it, and of course there were changes in concrete strength, the mix design. It's a mess. But so he used a simple calculation to determine the time-dependent deflections, and here are the results I'm showing you. And essentially, he covered all the data known at that time to within plus or minus 40%, which is damn good with respect to time-dependent deflections. And there was also another aspect of this thing. If you forgot about calculating the deflections, if you took the, oh, I'm sorry, I put that slide back. My apologies. We don't have to talk about that. But then the question arises, where does Gene get his genius? Now, I have a non-scientific hypothesis. That is non-scientific because you can't falsify it or you can't prove it. Look, in that small town in Urbana, Illinois, Talbot, a man who was born in a farm near Chicago, started an engineering experiment station. And he told his students very carefully, observe without a preconception. Observe without a prejudice about what you expect. Very difficult to do. I've tried to do it, and I find it very difficult. Then his student Abrams, even though he still is criticized by chemists, found a very simple relationship between the water-cement ratio and concrete strength, simply on the basis of observations and by a simple relationship. Richard, I think we should thank him for the simple way that we still design axially loaded columns. And this was the man also who tried to make sense out of the truss analogy, worked on it for 12 years, and admitted that it didn't work. Now, he might have said it works, but he admitted the truth. And then comes Cross, of course, that Tony talked about. And you know, he covered the whole ground. It is true that we recognize him mostly to his now defunct moment distribution method. However, it was his thinking that made the difference. About Richard's work on truss analogy, he said, look, just because the assumptions of a design method don't fit the facts doesn't mean the results aren't going to fit the facts. Go figure, huh? What he meant by that. But he was a brilliant man, and he carried on the tradition elegantly. We were talking about complexity. Hey, design of slabs is a very complex problem. But Westergaard took that complexity and made a simplicity out of it, which we still use today. It comes from Westergaard. And then Newmark. I mean, how can you say? Huh? That man's, I've always felt that he had some sort of a connection with the Almighty when he defined his method of calculating the relative deflection of a dam with respect to the ground during an earthquake. But nevertheless, he always made things simpler. I mean, it was a stream of simplicity flowing all the way through. And then Chet, well, you talked about him long enough, and that he tried to keep the code as clean and as far away from a textbook as possible, although he was not always successful. And by the way, you know, when Gene was the chair of 318, he surprised everybody because he didn't meddle in the work of the subcommittees, and he did not give long speeches. I thought that's one of his most delightful characteristics. Kindly listen. But So, insofar as I'm concerned, Corley was the jewel on that stream of sense that came through over the years, over 100 years in Urbana, Illinois. He was, in a way, a creation of that system. Not always, but most of the time, he managed to simplify things, but not always. Sometimes things got very complicated. Now look, he was also a lovely person who loved his family, who loved his friends, who loved his grandchildren. And if you will allow an engineer to write something as close as he can to a poem, that's how I would like to simplify his life. He was born in Illinois. He was a child of Clarence and Mary Corley, grew up in Shelbyville, fell in love with sailing and stayed with it, left Shelbyville for Urbana, fell in love with singing and stayed with it, fell in love with Lind and stayed with her, worked as an officer and then as an engineer, doted on his children and friends, always helped those who asked for help, and that he did in terms of organizational help, money help. He made grants to the University of Illinois and never gave up on what he thought was right. Sometimes what he thought was right was not right, but he never gave up on it. And I think will be remembered as a pioneer, if not the pioneer, in engineering forensics. And that's all I need to tell you. Thank you very much. Thank you.